Our next distribution is the Poisson. When we write Poisson, we always use a capital P because it's named after someone, Simeon Denis Poisson, a French mathematician. Poisson's also the French word for fish, so this guy is Mr. Fish. All right, so the way we use the Poisson is to model the number of occurrences of some phenomenon in a fixed period of time, or in space, or somewhere else, I guess. So for example, number of lightning strikes in a month, number of people who went to hospital because of an asthma attack, the number of rabbits you spot in the park. So, these are examples of things that could have a Poisson distribution. Key assumptions for something to be Poisson, the key assumption really is that the events you're counting are independent of each other. And if that's the case, then Poisson's going to work for you, actually. So the Poisson distribution, it's probability mass. It's a discrete distribution because we're counting number of times something happens. The sample space, the set of possible events is 0 or 1 or 2 or 3 or 4. And any non-negative integer is a possible value of the Poisson. Its mass function is either minus lambda times lambda to the power of x over x factorial. Lambda is the parameter of the Poisson. It tends to be a right-skewed distribution for small values of lambda, but as lambda gets bigger, it gets more and more symmetrical. And its mean can be shown with a bit of work. With a bit of work, you can show using some infinite series results from first year. You can verify that the probability mass function summed over all possible values is equal to 1, that the mean is equal to lambda, and that the expected value of the square of the random variable is lambda squared plus lambda, which tells us that the variance is lambda. So the mean is equal to the variance, and they're both equal to the parameter lambda if you have a Poisson variable. So where did this Poisson distribution come from? How did Mr. Poisson derive this bad boy? So we got some interval. We get lambda events on average in that interval. And we've got some random variable x. So I'm saying this is a random variable x, which is Poisson with parameter lambda. That's what we're going to say it is anyway. But how did we derive the probability mass function of x? Well, we know about the binomial distribution, don't we? So why don't we break this interval up into lots of teeny-weeny little sub-intervals. And we'll make these sub-intervals small, really small. In fact, we'll take the limit as they go to as the number of sub-intervals goes to infinity, hence their width goes to 0. So I'm going to have n of these. I've got n sub-intervals. I'm going to make them small enough that you only ever get 1 or 0 events in each sub-interval. So in this example here, I got 5 sub-intervals. I got 5 events. I got 5 events. And so, if I have at least 10 sub-intervals, that's probably going to be enough to break them up 1 per interval. But as my sample size goes to infinity, if I do this process and take the limit as n gets bigger and bigger, they will eventually get to the point where it doesn't matter what lambda is, doesn't matter how many I observe, you're going to get at most 1 per interval. But what's the chance? What's the distribution of number of events in here? Okay, so first of all, the width of this subinterval is 1 on n of the width of the total one. So if I'm getting lambda events in the whole interval, then I'm expecting lambda divided by n events per subinterval. Does that sound fair enough? Now what I'm going to do is I'm going to count the number of subintervals. I'm going to count the number of subintervals which have events in them. what's the distribution of y? If these events are independent, the number of subintervals that have an event in them is binomial, isn't it? I've got n subintervals, so the first parameter is n. What's the second parameter? Well, if we expect lambda on n of them per subinterval, if we're either getting one or none in it, then the probability of getting something in it is lambda on n. So what's the probability that y is equal to x? It's pretty funny writing it as y equals x, isn't it? The reason I'm doing that is because what I'm ultimately trying to do is find the probability that x equals x. And that's going to be the limit as n goes to infinity of the probability that y equals x, where y is binomial with parameters n and lambda on n. Okay? So it's the probability that y equals x. Just from the binomial thing, n choose x, lambda on n to the power of x, 1 minus lambda on n to the power of n minus x. All right? So now we take the limit of that as n goes to infinity. Okay, so let's re-express this probability before we start taking limits. The n choose x, I'm going to write as n factorial over n minus x factorial. And there's an x factorial in there too. I'm going to write that over here. The lambda to the x over n to the x, I'm going to put the lambda to the x over here. And the n to the x I'm going to put down here. And the 1 minus lambda on n to the power of n minus x. What am I going to do with that? I'm going to go the 1 minus lambda over n to the n over here. And I'm going to put that bit down here. If I've got room, I'll make a little bit of room for it. Okay, so this is kind of looking close now, isn't it? And so looking at this formula, we're nearly there. So we've got a lambda to the x over x factorial. This guy here, if you take the limit as n goes to infinity of this, it's e to the minus lambda through the exponential theorem. If you take the limit of this thing, well, this part over here ends up being basically n to the x. That part there we don't really have to worry about so much. And yeah, like these end up cancelling each other out, and the limit as n goes to infinity, that is going to have a limit of 1. That bit there, e to the minus lambda. And so there you are. That's going to be your answer. Okay, so we got this is a probability mass function of the Poisson distribution.